Welcome to NPTEL. Myself, Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Here, I show you a Bain correspondence for a face centered cubic to body centered tetragonal structure transformation. So, here face centered cubic is a austenite phase and body centered tetragonal is a martensite product phase. So, first please have a look carefully to this schematic. Here there is 2 FCC lattice. This is the first one and this is the second one. Please have a look at here. So, these are the iron atoms of the lattice 2 and here is the face centered atom. So, iron atoms are represented with a circular shape and the carbon atoms are represented with a square shape. Okay. Now, please clearly look at that. This is also a face centered atom, here is also a face centered atom, here is also a face centered atom. Okay. Okay. Now, let us go to the first one. Here is also these are the iron atom which are located at the corner and these are the face centered atom. Okay. This is an opposite side of the face and so on. Now, carbon atom here are located, carbon atoms here are located at the center of the edges. So, these are the edge of a FCC unit cell and carbon atoms are located here. You can have a look in both the lattice. And now, this is a face centered and now, if I join these face centered atoms, then what is going to happen? Let me change the color. So, I took this atom here, here and here, okay. And in the bottom also the same, okay. And then I can join them, okay. So, I get actually another new lattice by joining 2 FCC lattice of same structure and same configuration. Now, here this is actually A, okay, and here this is actually the distance. So, since this distance is smaller than A actually and these are the same distance, okay, okay, where only this is the C axis equals to A. So, it is a tetragonal lattice. Now, carbon atom actually occupy the octahedral sites, okay, because if you have a look why it is octahedral, okay, and then there is we can consider 1, 2, here is another one, here is another one and here is another one. Okay. So, 1, 2 in the opposite side, then total will be 8 actually 2 multiplied by 4. So, it will be a octahedral void. So, in that position the carbon atoms are present and therefore, this schematic of the Bain correspondence shows how a martensitic transformation occur without any diffusional movement of the atoms. So, the atoms remain in the same position, however, the lattice transform from a face centered cubic to a body centered tetragonal structure. This is very much interesting, and let us have a look at some other aspects. During vector analysis, I have told you that there is many different invariant shear involved in the process, and twinning necessarily to be formed during martensitic transformation. Okay. So, here I first show you a schematic of a austenite lattice. So, this is a austenite lattice, a small cell is shown here which looks like a square, and for martensite to form I have given a shear which is a homogeneous lattice deformation here, which is represented by a S vector. Okay. This is the net amount of the shear that is involved in this process. However, such shear we have seen in our last class for a single crystal how sample bend, okay, by this martensitic transformation. However, if we have a polycrystalline grain, okay, and this grain is a austenite and it is going to transform into martensite, then it has to be accommodated within that region, and we need to introduce some defect inside it. So, that the lattice strain or invariant strain has to be accommodated, and for that this same amount of this vector we can split into local domain in this way by introducing some dislocation. How is this process? I take the same lattice and I simply pass some dislocation here, here and also here, let us say. So, if dislocation pass from here to here, then definitely I will get such a step, is not it? Okay. And so, in a very small domain, by passing some dislocation, okay, I reduces and I accommodate the total strain, shear strain in this lattice. So, dislocation is a good lattice invariant invariant deformation process for martensitic transformation. Please remember that this dislocation we are talking about, it is not in the austenite phase, it is inside the martensite phase. Now, let us have a look to some other invariant strain which is commonly known as twin. So, twin looks like a mirror like plane of the parent lattice. Now, during this austenite to martensite transformation, these large shear can be accommodated into small domain by this way, that here is the twin. Okay. So, twin you can see this is just look like a mirror like plane. Please remember once again that this is also martensite, here is also martensite. Okay. So, two lattice invariant deformation we have discussed. The third one is that we can simply rotate the lattice, okay, so that we can accommodate the transformational strain. The third one is the rotation process, and schematically here I have shown you that not only dislocation have passed from this austenite to martensite transformation, this is the martensite lattice. However, we have introduced some rotation into it. Here is also a rotation is given, okay, along with the twinning. So, here you can see the twin. So, only one defect may not be necessarily involved in this austenite to martensite transformation, but a combination of two different invariant lattice deformation process may be involved into it. Okay. The fourth defect that may be involved in a martensitic transformation is the stacking fault. That is very interesting, and let us have a look at that. So, here this is an example of a stacking fault that has formed in a lattice during austenite to martensite transformation. Okay. So, this is a martensite lattice and this is the austenite lattice. Please have a look at this OP, that is the direction here. This is the parent lattice of 0, 4, 5 and which transform into basically 0, 0, 1 of martensite. M stands for here the martensite. Okay. And there is small fault is involved in these planes. You can have a look that how the faulted positions are there. So, here if you look at the OP here, this comes into the OP here. This is the A dash new position, this is the A dash, B dash, B dash, A dash and so on. So, it basically move little bit away which comes to C dash, again there is a C dash which is again C dash and so on. So, by introducing a stacking fault, we can accommodate the transformational strain, lattice strain in a martensite lattice. Okay. So, this is something interesting and we must look at some of the examples that how these transformation involve in those systems. Here I am talking about let us say the alloy system. So, martensitic transformation in case of a ferrous alloy means basically iron should be there and most commonly like carbon is present. So, let us say iron 0.4% weight percent of carbon. Okay. So, for a eutectoid steel it is 0.8. So, in a low carbon content face centered cubic which is the austenite and body centered tetragonal is the martensite. Okay. And here this is the orientation relation which of these direction and planes are the parallel to each other, and 1 1 1 of austenite is the known habit plane. Okay. And the defect structure or the substructure in the martensite involve the needles or lathe type, and here it involve with the formation of dislocation. So, the transformational strain in a low carbon martensite involve with dislocation density. Whereas, if you increase the carbon content, the crystal structure does not change in case either a austenite or in case of a martensite. However, you see the habit plane has changed. So, habit plane is not at all the same for all ferrous alloys, and here some twins will form along with the dislocation. Now, this is a similar situation for high carbon steel. However, it is also ferrous alloy, here this is iron and nickel. Okay. So, let us say something in between 27 to 34 weight percent of nickel is present, where face centered cubic is the same phase as the austenite, where BCC is the martensite. This is very interesting, right. So, austenite structure is same, but the martensitic structure is different. Okay. So, that is why I said earlier that martensitic transformation cannot be told only by the crystal structure of the martensite. Yes. So, how the transformation proceed that dictates whether it is a martensitic transformation or not. Now, you see this is a habit plane and mainly twinned, means along with twin some other defects like dislocation and some other will form. However, once again if carbon is present along with nickel, again it become body centered tetragonal. This is basically the martensite, okay, mainly twinned. And let us say in case of a iron copper alloy, these are let us say lathe and dislocations mostly present. So, we learned basically that in case of most of the ferrous alloys, even though twinning may form, but those are not so much dominating invariant strain in this martensitic transformation. However, we can also discuss in case of a non-ferrous system. So, I show you some of the common example of some non-ferrous system. So, the defect structure in martensite in case of a cobalt, titanium, zirconium or let us say lithium, here the austenite is the FCC phase in case of a cobalt, here this is BCC, austenite is BCC, whereas martensite is the hexagonal close pack structure, and in case of titanium it is hexagonal close pack. In case of zirconium it is also hexagonal close pack. In case of lithium it is also hexagonal close pack. These are all the austenite crystal structure. Now, the habit plane will vary to different system, where there are some stacking fault, mixed twin and dislocation they also form. So, if I look at the whole literature and various investigation so far people have performed, we mostly see that in case of ferrous alloy, since it is a gamma austenite phase, so it has a FCC crystal structure, and martensite in case of a carbon containing ferrous alloys are body center tetragonal. However, in case of a iron nickel system where carbon is not present, because it does not bring out with the tetragonality of the structure, that is why it become the martensite crystal structure is the body centered cubic structure. Now, in case of a non-ferrous system, the austenite is mostly BCC. However, there are few example of FCC also, and the martensite has a hexagonal close back structure. So, necessarily the austenite, which basically a phase transform martensitically to a martensite. Yes. So, that should be the definition of a austenite. We should not define by its crystal structure. So, austenite is a phase which martensitically transform into a product martensite phase, and martensite is also transformed from a austenite phase. So, a twinning is also is not necessarily the substructure of all the martensite in different system. This is also something very much interesting. So, besides twinning, there could be dislocation involved, there could be stacking fault involved, or there could be rotation of the lattice is also possible. So, there are so many different substructure that are involved to accommodate the transformational strain in case of a martensitic transformation. Now, let us try to look at how are the structure of the habit plane. The habit plane I said that is the invariant plane which remain unrotated and undistorted during the martensitic transformation. So, here this is a habit plane I am going to show you in case of a where dislocation slip is the lattice invariant shear. So, if a dislocation passes through a plane, then it is for sure that it will release the strain at the surface. So, there will be a zigzag surface. So, here this is the dislocation which release at the surface. So, these are the slip plane of the martensite, and dislocation has passed, and therefore, it basically shows you such kind of steps. Now, here this is actually the austenite. So, from austenite we are transforming into martensite, and there is a interface. Now, the interesting part here that if you look at the OA vector in this particular direction, the OA when it goes to martensite, it become O dash A dash, and you see the direction has also little bit change, because it is showing a up. Okay. Now, if I consider only the O and Z, okay, this is a large vector of another large vector, and then again if I join this O to Z dash, then they both looks actually the parallel. Okay. So, this means in a longer or large vectors, the habit plane does not change at all, and so on. A similar situation we can think about in case of a twinning. Let us have a look how this transformation goes on in case of a twinning. So, in case of a martensitic transformation where twinning is involved and invariant shear, you need to look at the structure from a austenite into martensite. Here this is the habit plane, and definitely here austenite transform into a martensite. The martensite accommodate the transformational strain by forming the twins. So, these are the twins. The question is whether these are the same twins or different directions are involved in this twin. Yes, there must be different direction, otherwise this has a different direction and this has a different direction. So, we represent here in terms of a type 1 and type 2 twin. So, usually type 1 twin is involved and originate from the mirror plane of the parent phase. Here parent phase is definitely the austenite one. However, in case of a type 2 twin where shared direction stem from the two-fold symmetry direction of the parent phase. So, it is important that twinning must be present, but the twinning may or the twin zones or the twin directions are different in case of a type 1 twin or type 2 twin. So, there could be other types of twin also form. I show you some of the example of in case of a copper nickel aluminum system and copper tin system. So, in case of copper nickel aluminum system, here type 1 twin is from 111 or O11 and type 2 twin is O11 types. So, we have seen that in case of a martensitic transformation where twinning is involved, there not only one type of twin accommodate the transformational strain, but there could be many different types of twin which has a different direction and different planes that are involved in order to accommodate the transformational strain. So, this is a very interesting and important information to understand the shape memory effect, which will be discussed later on. So far today we tried to understand the different transformational strain, how it is accommodated by different defects like dislocation or let us say like twin, like stacking fault, like rotation of the lattice. And here we also have tried to look at the structure of the habit plane, and we have surveyed a large number of ferrous and non-ferrous alloys, where we have seen that twinning merely form where dislocation dominant martensitic transformations are involved. And whereas, in case of some other systems like non-ferrous system, where the austenite does not have a face centered cubic or martensite is not at all body centered tetragonal like ferrous alloys. However, in those cases the transformational strain could be also accommodated by dislocation or a complex twinning. So, next class we will start with the shape memory effect. Thank you.